Welcome! In this video, I'll show you how to solve problem 2.18 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics, which is the same as problem 2.17 as it appears in the second edition of the problem. Now, this problem asks us the following. It says, well, it's got several parts, and basically what we are going to be doing, it's a pretty long problem, so I think I'll just read it whenever we go into a particular section. But what we want to do is familiarize ourselves with how we can get different Hermite polynomials. And why do we care about these Hermite polynomials? Right, these Hn. Why do we care about them? Well, as you might recall, what we have previously seen is the formula for the harmonic oscillator. And now that formula was something like this. So psi n of x, well, we could also write it in terms of psi, for example, which made the notation a bit cleaner. This is m omega. I'm just going to copy it. I don't know it by memory. This to the 1/4. And then we multiplied this by 1 over. So we already found this formula a few videos ago. If you're unsure where it came from, it is important that you have at least a rough idea. So go watch those videos. It's all in the playlist. And this is a formula that gives you the wave function for the solution of the quantum harmonic oscillator for any given n, right? So this is a very, very useful formula. You don't really need to know it by memory, but you have to know how to use it. And as you can see, the main difficulty here, because this here is a constant, this here only depends on n, so you just plug in n here and you already have this part. This is simply e to the minus psi squared over 2, so that's pretty easy. So the only thing is this polynomial right here, which is precisely the Hermite polynomial. So we need to be comfortable calculating the Hermite polynomial, okay? So there are several ways. I already showed you in a previous video how to calculate it like manually, but now we're gonna start seeing some very, very useful theorems and formulas that there are. So we're gonna start off with part A, where we will be discussing the Rodriguez formula. Now, the Rodriguez formula states that the nth Hermite polynomial is the same as taking -1 to the nth power, multiplying by e to the psi squared, and then taking the nth derivative with respect to psi of e to the minus psi squared. And we can use that to derive h3 and h4. Now that sounds like a lot, it sounds like a mouthful, but that's actually not difficult at all. So let me show you how we can do that. So let's go for h3 first. I'm going to copy the formula here because I'm going to scroll down and I might lose visibility of the formula that is up there. So -1 to the n, e to the psi squared, d psi nth derivative, e minus xi. Okay, so we want to find h3 and h4. So h3, and notice that what we're going to do here is we're going to find, actually maybe let's keep the notation, we're going to find h3 without having to know anything else, right? We don't have to use any sort of recursive formula. This is going to be extremely powerful. So let's just plug n equal 3. So we get -1 to the third power, which is -1, times e to the psi squared. I'm very bad at drawing psi. d psi, then cubed, or well, not really cubed, but rather the third derivative, and e to the minus psi squared. So let's take 3 derivatives of e to the minus psi squared. So one derivative, the psi of e to the minus psi squared, this is simply -2 psi e to the minus psi squared. Now, second derivative, this is simply going to be, well, we have 2 parts now. So by the product of the rule of product, we get -2 e to the minus psi squared, and then a second term, which is going to be what we already had, which is -2 psi, times the derivative again, which is -2 psi again. So we get this thing squared, which is going to be plus 4 psi squared, and then e to the minus psi squared. but we still need to derive this once again. So let's go for d cubed e to the minus psi cubed. So we now derive this. The first term we get 4 psi e to the minus psi squared. Here now we have, once again, two parts. Let's derive this thing first. So we get 8 psi e to the minus psi squared, and then minus, now we're going to multiply this, we get 8 psi cubed e to the minus psi squared. And notice we can add these two together. So instead of having both of them, we can just write 12. So we have 12. Okay, so now we have this part. Let's plug it in. So let's get rid of this. And we plug it in. We have 12 psi e to the minus psi squared minus 8 psi cubed e to the minus psi squared. And now the exponentials will cancel each other out, and we are left with 8 psi cubed minus 12 psi. And this is our third Hermite polynomial. There we go. It was relatively easy. I mean, considering that we didn't have to use any sort of recursive formula, it was very, very simple. Of course, we did have to derive quite a few times, which can be a little bit annoying, but it's definitely better than the alternative. So this is the third Hermite polynomial. And notice, as we had seen before, that when n is odd, the powers of psi are all odd. As you might recall, we discussed that when we were deriving the Hermite polynomials for the first time when we solved the quantum harmonic oscillator. So that's an interesting thing to consider. Now let's go for H4. H4, the fourth Hermite polynomial, or Hermite polynomial of the fourth order, this is going to be, now let's go back to the formula, minus 1 to the nth power, which is simply 1. Then we have, well, e psi squared. This is always here because it needs to cancel out the remaining e minus psi squared. There is no exponential in the Hermite polynomials. It's simply a polynomial. So that's why that exponential is here. It cancels out this thing. And then we have the fourth derivative. So this is basically e minus, to the positive psi squared times the fourth derivative. But that's quite easy to calculate because the third derivative is right here. So we simply have to derive this one more time. So let's do it. We have two terms coming from this and two terms coming from this. So from the first one, we get 12 e to the minus psi squared, and then minus 24 psi squared e to the minus psi squared. And now from this term, we get, deriving first this, we get minus 24 psi squared e to the minus psi squared. And now from the exponential, we get plus another minus sign. Now we multiply by 2, so we get 16 psi to the fourth power e to the minus psi squared. Now, of course, the xi's will cancel, the exponentials will cancel each other out again. And now we can add these two together. So H4 will be 12 minus 48 psi squared plus 16 psi to the fourth power. Nice. So as you might see, this is an even n, and thus we only have even powers of psi. We have psi to the 0th, which technically is not even or odd, but you know, it counts in this case because we're going 1 and 1, right? Even, odd. So we can put it with the even powers. So yeah, you know, just so that you see that this is indeed making sense. So that is part A. That was pretty simple. All we had to do is use that formula, which might look intimidating, but it's actually really simple. Now we have the following recursion relation, which gives us the n plus 1th Hermite Hamiltonian, Hermite polynomial in terms of the two preceding Hermite polynomials. Okay, so this formula, I'm going to write it down here, maybe here. So the formula is as follows. So part B, that is the n plus 1th Hermite polynomial, or Hermite polynomial of order n plus 1, as it's the same. This is 2 times psi times the nth Hermite polynomial minus 2n times the n minus 1th Hermite polynomial. So you might see how this differs. So this time, we need to know 2 of the polynomials before we can even use this formula. In part A, we could simply use this formula, and it didn't matter if we knew what the preceding polynomials were or not. We didn't need anything. But the problem, or what is annoying, is that we have to take many derivatives. So for example, if you want to find the 100th Hermite polynomial or something like that, it's going to be pretty annoying. You're going to have to do it a lot. But if somehow you know 2 others that are one next to the other, they are contiguous, then you can use this recursion formula. So we need to use that formula to obtain h5 and h6. So h5, if we want to find h5, it means that n plus 1 has to be equal to 5, right? Thus, n has to be 4. So h5, which, as I mentioned, corresponds to n equals 4, is going to be 2 times psi times the 4th Hermite polynomial minus 2 times 4 times the n minus 1, so the 3rd Hermite polynomial. Okay, so we already know both of them. This right here is the 3rd one, so let's plug it in. So actually, let's go for the number 4 first, because it appears first. So h4 is 12 minus 48 psi squared. So this is 12 minus 48 psi squared plus, and I already forgot, 16 psi to the 4th power, plus 16 psi to the 4th power. And notice that we're going to find h5, which is, of course, odd. So we need to have only odd powers of psi, and that is precisely what this psi right here is doing, right? Just so that you keep that in mind. Minus 2 times 4, which is 8, so maybe let's just write 8. And now we multiply by h3, which is up here, which is 8 psi cubed. Or maybe let's write it like this, so it's in growing order. So minus 12 psi plus 8 psi cubed. Of course, it doesn't matter which one you write first, but it might be a bit more, or look better if we, and be a bit more organized if we go with the lower powers first. Okay, so let's multiply. So multiplying, we get 24 psi minus 96 psi cubed plus 32 psi to the 5th power, then plus 8 times 12, which is 96 psi, and then minus 8 times 8, so we get minus 64 psi cubed. So now let's add everything together. So 24 plus 96, that's 120. Then for psi cubed, we have 96 minus 64, so both of them negative. So we get minus 160. And then finally, we have plus 32 psi to the 5th power. So this was really, really, really easy, as you can see. But it required that we knew 2 other Hermite polynomials, which we don't always do. Okay, so these formulas, of course, are limited. Now let's go for h6. h6 we will solve in the precise same way. So exactly the same, but of course now with different n. So for if you want to find the 6th one, we need n plus 1 has to be equal to 6, which means that n has to be 5. So plugging n equals 5 to the formula, we can find that the 6th, right, the n plus 1 Hermite polynomial of psi, this is going to be 2 times psi times the nth Hermite polynomial, n is 5, minus 2 times n, in this case n is 5, times, and this is n minus 1, so h4 of psi. Now we already know h5 and h4, so let's plug them in. So 2 psi, h5 is this thing right here. So it is 120 psi minus 160 psi cubed plus 32 psi to the 5th power minus 10 times h4, which is this thing right there. So that is 12 minus 48 psi squared plus 16 psi to the 4th power. So now let's simply multiply through. So we get 240 psi squared minus 320 psi to the 4th power plus 64 psi to the 6th power minus 120 plus 480 psi squared, and then minus 160 psi to the 4th power. So let's put all the powers of psi together. So 0th power, we have 120. Then squared, we have 240 plus 480, which is 720. Then to the 4th power, we have minus 480. And finally, we have 64. So there we go. As you can see, this method is really easy, but as I've said, it requires you to have other information, which you might not always have. Now, part C, it says if you differentiate an nth order polynomial, oh, I made a typo there, you get a polynomial of order n-1, right? As always, if you have dx of x to the 6th, you get 6x to the 5th, right? Nothing new there, we know that. In the case of the Hermite polynomials, we can actually get a lower order polynomial. So for example, if we have the 6th order polynomial, we can find the 5th and so on. And what they want us to do is to check this by differentiating the 6th and 5th Hermite polynomials. So let's do that. So what the formula here says, I'm going to write it down here and we're going to do part C. So the formula that we saw says that if we take a Hermite polynomial of the nth degree or nth order, and we take the derivative with respect to psi, then we will get 2 times n times the Hermite polynomial of 1 order less. So let's check this by using the 6th order Hermite polynomial that we just found. So it is this thing right here, right? This is h6. So let's take the derivative with respect to psi. And if you do that, well, the first term, it's going to be 0. The second will be 2 times 720. So 2 times 720 times psi. Then we get minus 4 times 420 psi cubed. And then we have plus 6 times 64 psi to the 5th power. And this has to be equal to 2 times n, which is 6, so 2 times 6, the 5th order. Okay, so we have to divide this entire thing by 12, basically. So if we do that, let's see. We can simplify this 2, we can turn this 4 into 2 times 2 and get rid of one of them. And also this 6, we can write as, actually, we can just cancel it with this. And this will be 32. And we have to divide this by 6, which is 80. And then this divided by 6 is 120. Okay, so h5 of psi, this is 120 psi minus 2 times 80, which is 160 psi cubed, and then plus 32 psi to the 5th power. And we have already found it, so let's double check. h5 is 120 psi minus 160. Yeah, the exact same thing. So let's now test it with the 5th Hermite polynomial. Now, in this case, what is the 5th Hermite polynomial? It's what we just found here, so let's derive it again. So we get 120 minus 3 times 160 psi squared plus 5 times 32 psi to the 4th power. And this has to be equal to 2 times 5 times h to the n minus 1, which is 4. Kind of looks like a 9, I guess, so maybe I should be more careful. Okay, so basically now we divide this thing by 10, so we get 12 minus 3 times 16, which is 48. And then plus, and here dividing by 10, this goes away, and this is now 16, so we get 16 psi to the 4th power. All right, so let's check. Where is h4? h4 is this thing, 12 minus 48 psi squared plus 16 psi to the 4th power. So it is indeed correct. Now, finally, they say the nth order Hermite polynomial is the nth z derivative at z equals 0 of the generating function e to the minus z squared plus 2z psi. Or, to put it another way, it is the coefficient of z to the n over n factorial in the Taylor series expansion for this function, for the function that we see right here. So basically, this is what they are telling us, and we want to use it to rederive h0, h1, and h2. Okay, so that one looks very intimidating. I'm going to move everything to the side here. There we go. This looks very intimidating, but don't worry, it isn't that bad. So there's two ways to go about it. I'm going to show you what I like to do here. So there's a few ways to think about it. Let's write down the function that they say. They say that we can use this function to generate the Hermite polynomial. So e minus z squared plus 2z psi. This is equal to the sum from n equals 0 to infinity of z to the n over n factorial and the nth Hermite polynomial. I forgot to write down the psi there. So this is what they are saying. Now let's write out the right-hand side explicitly. And we can write this part explicitly. So when n is equal to 0, we have z to the 0th power, the 0th order Hermite polynomial, and 0 factorial, which is 1. So we get simply h0. Then for n, I'm going to write it here, n equals 0. N equals 1, we get z h1 psi over 1 factorial, which is 1, of course. And for n equals 2, we get z squared h2 of psi 2 factorial, which is 2. And then for n equals 3, we get z cubed h3 of psi divided by 3 factorial, which is 6, and so on. Now, what about the left-hand side? Because we have here this sum, basically, that we have set out of these infinite terms. Now, let's write this exponential as the Taylor expansion of said exponential. Now, how do we write a Taylor series, just as a quick reminder? So let me quickly remind you of what the Taylor expansion looks like in case you have forgotten. So if we have some function, in this case, let's call it f of z, since we are already going to be dealing with z, and we want to expand this as an infinite sum of terms, we can do it as the sum of n equals 0. Actually, we already are using n here, so it's probably best to use a different letter just so that there's no confusion. So let's say m. So m equals 0 to infinity of the mth derivative of the function evaluated at some number a. In this case, we are being told that it is at z equals 0, so a is 0. But in general, of course, it could be anything. So we are dealing with the Maclaurin series here. And then we multiply this by z minus a, but again, z is 0, a is 0, sorry. So that means that we get z to the n. and this thing divided by n factorial. M. Okay, so that's the Taylor series. So let's write out the Taylor series for the exponential, at least the first few terms. So we're going to need the derivatives. So this is going to be e to the minus, or maybe let's put it in general first. So we get that f of z, which of course is our exponential. This is going to be the 0th derivative. So I guess we just don't write it, right? Z to the 0 mth, which is 0 factorial, so 1, plus first derivative evaluated at 0 times z divided by 1 factorial, which is 1, plus second derivative, let's write it like that, evaluated at 0, z squared divided by 2 factorial, which is 2. Then we get f derived 3 times evaluated at 0, z cubed divided by 3 factorial, which is 6, and so on. Okay, so let's find each one of the derivatives. So what is f prime evaluated at 0? So this is the derivative with respect to z of e to the minus z squared plus 2z psi. Should I do it like that? Okay. So this is an exponential, so the derivative of the exponential is the same, but because of the chain rule, we need to multiply by what is inside. So this is minus 2z plus 2 psi times, of course, the exponential, minus z squared plus 2z psi. And now we have to evaluate this at z equals 0, right? This evaluated at z equals 0. So when we do that, this z here will be 0, and the exponential will go to 1. So we get simply 2 psi. Okay, so the second derivative, so f2, this will be the derivative of this, and then we have to evaluate it at 0. So the derivative of the parentheses will be minus 2 e minus z squared plus 2z psi plus the parentheses minus 2z plus 2 psi times the derivative of the exponential. But the exponential will simply give us this parentheses again, so we can square it, and there we go. And we have to evaluate all of this at z equals 0. So when we do that, this exponential, well, it's 1, so we get minus 2. And this thing right here, z here, it's 0. So we are left with 2 psi squared. So plus 4 psi squared. And there we go. That's the second derivative. Now, finally, we need one more derivative. So we have to derive this thing here. Now, to do that, it's going to be useful to write this out explicitly. So write it as 4z squared plus, actually minus 4, let's see. Actually, no, it's 8, because we have this times 2. So minus 8 z psi plus 4 psi squared. And all of this times the exponential, this one. Okay. So the third derivative, evaluated at 0, that's going to be minus 2 times, from this one, minus 2z plus 2 psi e to the minus z squared plus 2z psi. And now from this part, we get plus. Now here we get 8z minus 8 psi, and this 4 psi squared just goes away. It doesn't depend on z. And then we get the exponential, minus z squared plus 2z psi. And then we get another term, which is going to be this thing, right, which was the same as this, but now multiplied by itself again. So we get minus 2z plus 2 psi cubed e to the minus z squared plus 2z psi. And now we have to evaluate all of this at 0, which makes it a lot easier. So all the exponentials are going to go to 1. This goes to 0, so we get minus 4 psi from here. Then this is 0, so we have minus 8 psi. And then this is 0, so we get 2 psi cubed. So we get plus 8 psi cubed, which is minus 12 psi plus 8 psi cubed. There we go. So now we have all three derivatives. So let's plug them in here. Okay? Because we know that this expansion, right, we can take this exponential and expand it as a Taylor series. So I'm going to write it out explicitly first. So this exponential, I'm going to write it as 1 plus f prime, right, the first derivative evaluated at 0 times z plus f derived twice evaluated at 0, z squared divided by 2 plus f derived 3 times evaluated at 0, z cubed, and this is divided by 6, and so on. And this has to be the same as this thing right here. So that has to be the same as h0 of psi plus z times h1 of psi plus z squared of h2 of psi plus z cubed of this is divided by 2, by the way, h3 of psi divided by 6, and so on. So what we can see here is that we have very similar thing on both sides. And if we want these things to be equal, we need each power of z to be equal. So we need h0 of psi equal 1. We need h1 of psi to be equal to f prime evaluated at 0, which we already know is 2 psi. h2 evaluated at psi, this is f2, right, twice derived, and that is minus 2 plus 4 psi squared, so minus 2 plus 4 psi squared. h3 is, let's see, minus 12 psi plus 8 psi cubed. And that's how you can find them, find the Hermite polynomials using this formula. And that's also why you can see that they also said that the Hermite polynomial is the nth z derivative at z equals 0 of that function, right? So we took a few extra steps by taking a look at this, just so that you could understand why that is. Because when you expand this in terms of in the Taylor expansion, both sides will be multiplied by this part. So you will always end up with the derivative is equal to the Hermite polynomial, okay? And which is what we saw right here, right? We expanded this, and this is common to both sides, right? Z divided by 1, Z divided by 1, Z squared divided by 2, Z squared divided by 2, right? It's always the same. The only difference is this derivative versus the Hermite polynomial. Actually, I just noticed I didn't have to calculate h3, but well, I mean, I guess there it is. We calculated h3 for you just in case you were interested. We can even check if it's correct, I guess, because we found it before. h3 is 8 psi cubed minus 12 psi, so yeah, it is indeed correct. All right, so there we go. We just solved problem 2.18 or 17, depending on the addition. And you can see it wasn't anything too terrible, and I hope that it was useful to you so that you can be a bit more comfortable when dealing with the Hermite polynomials. So thank you very much for watching. I'll see you in the next video.